I'd like to introduce thank you very much. Purdue always gets the best guests. Ronnie has been supporting us for years as well as NVIDIA in general. So I feel like it doesn't need much introduction. But I should like to say, as a computer gamer back from the Riva TNT days of really first GeForce One and all the rest of it, I followed the development and now into the AI era. It's fantastic to be able to have him come and describe to us literally how the world is being changed on a moment-to-moment basis. So, Ronnie.
Thank you very much. So, I think we're going to start off with the agenda. I'm going to talk to you a little bit today about, briefly touch on AI. How many of you have heard of AI? All right, fair few of you. So how many of you know what AI is built on? GPUs, yes, right answer. So I'm going to explain to you why AIs are built on GPUs. But of course, processing units have been around for a long time. A graphical processing unit, even though it's been around for a long time doing exactly what it says, processing graphics, wasn't thought of as the foundation of AI. So I'm going to talk a little bit about the difference between a GPU and a CPU, and also explain why AI is adapt to GPUs. At the end of this session, we also have a few minutes as well where one of our university recruiters, Kat, is going to come on and talk a little bit about engaging as a student with NVIDIA and how you can do that. But let's start off, should be a video. Okay, here we go. I think this is it.
This is how intelligence is made. A new kind of factory. Generator of tokens. The building blocks of AI. Tokens have opened a new frontier, the first step into an extraordinary world, where endless possibilities are born. Tokens transform words into knowledge and breathe life into images. They turn ideas into videos and help us safely navigate any environment. Tokens teach robots to move like the masters. Inspire new ways to celebrate our victories.
A martini, please.
Tony, light up.
Thank you, Adam.
And give us peace of mind when we need it most.
Hi, Maroka.
Hi, Anna. It's good to see you again.
Hi, Emma. We're gonna take your blood sample today, okay?
Don't worry. I'm gonna be here the whole time.
They bring meaning to numbers to help us better understand the world around us. Predict the dangers that surround us. And find cures for the threats within us. Tokens can bring our visions to life. And restore what we've lost.
Zachary, I got my voice back, buddy.
They help us move forward, one small step at a time. And one giant leap together. here is where it all begins.
That was the NVIDIA headquarters in Santa Clara in California, where I go into work every day. But all of those are real examples. And if you think about with 3 years really into the general AI journey, you can imagine what's going to happen over the next few years. But let me turn to a little bit about who NVIDIA is, what is underneath all of these applications. NVIDIA is really, think of us as a full stack computer company. What do I mean by that? I'm going to talk a lot more today about the GPU and the CPU. You can see that's just 2 elements, but 2 very, very important elements that enable us to deliver all of those applications that you saw, and for our partners and our ecosystem to deliver that. Every year, we deliver a new version of that GPU. We also build CPUs. We also build data processing units and network interface cards and complex switches and system on chips specific for certain applications. So a lot of silicon at the foundation of this computer architecture company. On top of that, we build the systems. These are the servers and the systems that these GPUs and other silicon go into. And then we build the programming environment with the libraries that enable you to program this silicon. So NVIDIA has to deliver this full stack for these applications to be built. But we work with thousands and thousands, in fact millions, of developers around the world who are not part of NVIDIA, and give them access to these tools and technologies. So the design environment of CUDA and CUDA-X, which is the accelerated version of CUDA, millions of downloads around the world. Some of you may already have been programming in CUDA to gain the performance of the GPU. What I wanted to do today is talk a little bit more about the silicon that underlies this full stack. But keep in mind, it's a full stack that as you go through your learnings, you're going to have to understand how the silicon, well, not have to, but it will be beneficial for you to understand how the silicon can interact with the software. So firstly, a CPU is a central processing unit and has been around for decades. It contains several cores. Initially, it only had really 1 core. It was a single core central processing unit. What it does is it programs in a serial way. It executes functions. And think of it as you execute a function, the output of that function, you then go to memory, or you pull data from memory, and you either putting data in memory or pulling data from memory. Then you go to the next function, and you execute that function. And so over time, the silicon improvement that started to happen generation to generation enabled you to perform those serial functions much, much faster. And so, as I said, good for serial processing can do maybe a handful of tasks. And you start to think about, as memory is being called from either local memory, cache memory, as in-system memory, DRAM memory, or cold storage memory, SSD, or drive memory, you can start to see how multiple functions can be executed within the same clock cycles. And clock cycles is important because what happened over the years is those clock cycles improved from a few megahertz to a gigahertz or so. So the silicon speeded up as well over time. So, as I said, the general purpose CPU is composed of a few cores handling a few software threads at a time. Now, along comes a graphical processing unit, probably about 30 years ago. The GPU was designed to implement a graphics pipeline. And as you think about a graphics pipeline and you think about visuals coming up on the screen, you want all those pixels to come up at a certain refresh rate at the same time. It's very important that all of that processing for those pixels and how those polygons are organized happens at the same time. And so a new type of processing unit was created, and that is many cores, high throughput, and really excellent at parallel processing, all around the same clock cycle, so everything happening at the same time. So it can do thousands of operations at once. Now remember, this is going back 30 years. So it's taken a long time as we go through both of these cycles to get to where we're at today. And I'm going to talk a little bit about where we're at today. The first thing that many of you have heard of is Moore's law. Hands up who's heard of Moore's law. Okay, good. So Moore's law was described essentially every 2 years, every 18 months, a 2x improvement or a 2x cost benefit, depending on which law you're actually looking at. But as we started to see, we saw Moore's law providing this level of improvement. But what did you start to see here? This is John Hennessy, who was a professor at Stanford, a computer architecture professor at Stanford, who described this in his book and said the end of Moore's law and the future of computing. What started to happen here is you started to see a plateau. Dennard scaling, how many of you have heard of Dennard scaling? Okay, you should go look that one up. That's important. That's about power and the ability to leverage all the silicon based upon the power consumption. There might be a question on Dennard's law, maybe. And then as we go through that plateauing, you realize that the accelerated compute required for some of these new graphics and new AI can't be achieved with CPUs alone. And so what started to happen is, even though you see what's called reconfigurable wave, and there's many, many companies that were in this reconfigurable wave, one of those companies that was in that reconfigurable wave is a software reconfigurable technology, which is a graphics processing unit. And as you see, this is a simplification of that graph. You see Moore's law plateauing. You can see the GPU performance increasing 1,000x in 10 years. What do you do then in software architecture is you have to start offloading certain functions into the graphics processor unit. Those functions you need to accelerate, and they need to be optimized and optimal for parallel processing. Matrix multiplication is one of those, some of those math that parallel processing is very, very good at. And what forms the basis of modern deep learning is matrix multiplication. So this is what started to happen as you start to see silicon geometries and the lifetime of silicon start to increase. The silicon roadmap didn't slow down. We were still able to achieve significant enhancements in the dimension reduction. You're going to hear a lot about that from companies like ASML and lithography and other areas on how they're able to continuously shrink the size of a transistor. As you shrink the size of a transistor, of course what you start to get is you start to get higher leakage currents, you start to get more current burn, and so you don't put as much voltage on the chip. So what started to happen is the VDD, or the voltage on the chip, started to not go down as much. So today, chips consume a lot of power. That power has to be dissipated. And that's a very important part of how do we design those chips that you saw on the bottom of that stack. So think about modern computer architecture. Modern computer architecture really is a combination of a GPU and a CPU. Certain tasks lend themselves to single-threaded or serial processing. Certain functions and tasks lend themselves to parallel processing. We all know, I've already explained about graphics, about matrix multiplications, about some linear algebra that lends itself to parallel processing. As we start to see the computer architecture build up with these two components, we start to see other things become important as well. This DDR interface to the system memory. We start to see how do you have a link that's very fast and low latency between the CPU and the GPU. These two things take a lot of innovation as well. DDR improves every generation of silicon. A lot of IP, intellectual property, goes into this DDR interface. And of course, you want to make it a standard in the industry. Because if you're getting your system memory from, let's say, an SK Hynix or a Micron or a Samsung, you want to have that same interface behave in the same way. And so they standardize around that DDR interface. Here, this PCI interface has become a standard. You can see in many servers you have a PCIe card. In fact, graphics, you have an NVIDIA card that you put in a PCIe slot. That PCIe slot creates latency as well. But it's we're now at PCIe Gen 5. That improvement of latency improves every generation. Latency, just by, I think maybe I'll explain it for a minute. Latency is the round-trip delay, essentially, of a signal. How long it takes to send a signal and receive a signal. And we're now in the form of nanoseconds. But it's still appreciable if you think about clock cycles running at gigahertz. So now what we're doing through our design environment, if you remember CUDA, our design environment now enables you to design functions that can be split between this CPU and the GPU and optimize the amount of memory you need within that environment. So CPUs remain essential. GPUs break complex problems into thousands or millions of separate tasks and enable them to run all at the same time at once. The two devices are connected. In NVIDIA, we found that we could develop a better interface than PCIe. We call it NVLink, NVIDIA Link. Runs at 900 gigabits per second in today's technology, and very low, what's called picojoule per bit. How many bits are you transferring over that link, and how many joules or picojoules does it take in terms of power to transfer that bit? So about 2012 is when some very innovative students, PhD students from Toronto University, went down to New York and lined up to get their hands on some of the first released GPU cards. They took those, went back to Toronto University. They were studying under Professor Hinton, who is thought of as the godfather of AI. And what did they do? They developed an image classification algorithm using deep learning. And they entered a competition called ImageNet, and they won it by 100x. And so was born deep learning. And that's the foundation of AI. So since then, NVIDIA has recognized that GPUs have become a key enabling technology for deep learning. And think of deep neural networks in terms of layers. what was once one layer. This is just the way your brain works, connecting neurons in your brain as you're learning things. Hopefully a few neurons are connecting in today's lecture. But as you're learning these things, you're starting to fuse those connections. We now go into tens, if not hundreds, of the layers. And think about the parallel processing required to do that level of learning at one time. So deep learning pours vast quantities of data through neural networks, training them to perform tasks too complicated to be able to do in single-threaded or serial processing. And the Compute Unified Device Architecture, as I said, CUDA, is a parallel computing platform that lets coders take advantage of this architecture. So as you can see, CPU and GPU exist together. Type of applications that we're starting to see, you saw the video at the start. All of those are real-world examples, but within that you saw image and voice analytics. You saw robotics. Training robots is very, very difficult task. If you think about training a robot to do either a delivery drone or the robots that actually deliver food around campus here, training those things is quite difficult. Large language model training. The world has woken up to generative AI and the concept of large language models, and now even waking up to things like DeepSeek, which are reasoning models, all built on GPUs and all using GPU parallel processing. Speech recognition and instant translation. Soon, not too far, we're already starting to see you have an earphone and you start to hear instant translation. And then recommendation engines have been around for a long time. Recommendation engines are essentially when you go onto a website and you start buying things, or it knows where you are. If you know, it says, can you share that location? You'll start getting recommendations of things to buy based upon your location, based upon what you've bought in the past. That's AI at work, providing you recommendations. So now, imagine deep learning neural network, multiple hidden layers, process these hierarchical features. From this, you determine this. That was one of the breakthroughs of deep learning, is that you don't have to train with numbers of pictures. You can start to recognize edges and features as you're connecting these layers of neurons together. Again, all done in the parallel processing of a GPU and storing it in that DDR memory or cache memory. So the computer architecture is so fundamental to enabling AI. And then below that computer architecture is enabling the transistors to give you the level of performance you need at the level of power that you can deal with. Today, we're talking about kilowatts of power for racks of these computers. Even liquid cooling required. Many have air cooling, but liquid cooling for the new generation of computers is required. So all the way up from the transistor, the leakage current, the optimization voltage running on the transistors, all the way up to the computer architecture enables things like this to be done. So what we're able to do now is this new era of generative AI. We've now turned out, within NVIDIA, turned new models. The latest GPUs include tensor cores in the silicon themselves. These are cores that are designed to do these functions more efficiently. We're also embedding what's called transformer engines. Transformer engines form the basis of generative AI. We're able to go between text and animation. If you type a text in to say meta.ai or whatever your personal generative AI choice is, you get an image out. You're going from text to image. You're able to create videos, text to videos. Why? Because the world is described in certain ways. Colors and videos are on the Pantone scale. You can look at combinations of those things. So the largest GPUs look a little like this. I showed you a diagram before, but this is really a rendering of one of our latest GPUs, which is called Blackwell. Blackwell is manufactured at TSMC on their 4NP process. It's customized for NVIDIA, of course, with 93 billion transistors and a chip size of 750 square millimeters. What you can see here are actually memory, HBM, high bandwidth memory that's connected at high speed to this large chip. And then, remember what I said CPUs and GPUs are required? What we did at NVIDIA is we put a GPU, two GPUs, and one CPU on the same board, and this is what's called Grace Blackwell. It shares the same memory, and so that means it's exceedingly fast with doing those memory calls and fetches, that you don't have to go over a PCIe bus, for instance. Am I getting a time check? Okay, good. So as we go through this generational improvement of GPU, CPU, it's not slowing down anytime soon. Last week we announced our roadmap, some of you may have seen. Every year we're producing a new GPU family, and those CPUs as well. We're also having to put these GPUs and CPUs in very, very complex packages. And that's because there's a lot of power dissipation, but there's a lot of challenges in packaging. There's resistance, there's capacitance, and there's inductance. All of that needs to be optimized to bring that speed out. And we have to be able to take the package, we have to take the thermals out of the package as well. And so the latest GPUs are designed with the latest silicon packaging technology called CoWoS, which is from TSMC. They're also designed with EDA tools, latest industry electronic design automation tools. That comes from companies like Synopsys or Cadence. These tools are very important into being able to make sure that the silicon is designed right and it comes out working first time, because there's many interactions on this silicon that can prevent that from happening, and those all need to be comprehended. The way we do that is with our design methodology in something called emulation and verification. Basically, we run the chip design through emulation first, which is large computers that run very slowly. So we can have that entire chip running on hundreds of servers. And so we figure out how that chip's going to run, and we start running software even before we tape the chip out. And verification is making sure that we actually have that chip working. Okay, I thought I'd quickly show you a video that shows you how somebody else thinks about the difference between a GPU and a CPU.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen, Leonardo 2.0. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9, 8, 7, 6, 5.
So this is parallel processing.
3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
I thought that would be a good way of showing the difference between serial and parallel processing. Maybe I'll hand it over to Kat now.
Thank you so much. If you want to go ahead and advance the slides, that'd be great. So my name is Kat. I am what they call a campus manager at NVIDIA, and I basically oversee the recruiting relationship between Purdue and NVIDIA. So I'm basically the conduit between yourselves as candidates, the recruiters, and the hiring managers, and it's an honor to be here today. I will be in the next slide if you want to move forward. I also will have a link that you can click if you'd like to register to keep in touch about upcoming opportunities with NVIDIA. We are wrapping up our hiring for the summer, but I'm happy to stay connected when we start opening up applications, usually in August or September. So if you want to go to the next slide. We had an amazing conversation with Ronnie about the technologies that we work on, specifically CPUs and GPUs. But what I want to highlight really quick are just some of our core values that help you understand. Now you know what we do. I'd like to help you understand kind of what makes us tick. And so one of the core values that I would like to touch upon first is our commitment to innovation. And I love this core value because we strongly believe in identifying problems that no one else can solve and coming up with really, really amazing solutions for how to solve them. We work with some of the greatest minds in the industry, and I love being a part of this innovative culture because I am rarely the smartest person in the room, but we are surrounded by innovative, passionate people that are committed to getting work done. And then I also love our commitment to one team. And so at NVIDIA, we consider this a place where no one fails alone. So we work really hard on problems. And when things start to go wonky, it's never one person's fault. The whole team is involved to troubleshoot, solve, and come together and overcome whatever challenges we may face, whether they be technical, personal, or professional. So it's a really supportive, amazing culture to be a part of. So on the next slide, there are 3 main points of entry into NVIDIA as a college student. And it begins, the first is our pre-internship program, which is called Ignite. As I mentioned, our application window for Ignite is now closed, but this is set aside for freshmen and sophomores who are pursuing their bachelor's degree and will be graduating in 2028 or 2029. We will be opening up applications again in September for our 2026 summer intern class. As an Ignite intern, what you can expect is just like our regular interns, you are assigned a mentor, you'll work directly with your hiring manager, but you are part of a special cohort of interns where we also surround you with opportunities to network with your cohort, to get professional development, how to navigate a corporate culture, as we acknowledge this may be your first time actually entering into the professional world. And so this is a great opportunity if you're interested in learning more about NVIDIA, our technologies. Our Ignite interns, just like our regular interns, actually work on real projects and solve real problems that we are trying to solve. But again, it's with a tighter knit community and a lot more high touch, making sure you are supported from day one until your last day. As I like to say, there's no such thing as a no. There could be, just not yet. So if you don't happen to get into our Ignite intern program, you can always enter as a standard or normal intern. So that can happen. Basically, in order to qualify for an intern at NVIDIA, you just have to have plans to return to university at the completion of your internship. Most of our interns tend to join us in the summer, but we do offer off-cycle internships in the fall, winter, and spring. And I do know that Purdue can lend itself to co-op opportunities. So if that's something that you can do with your academic schedule, we're happy to work with you on that. Our interns, again, work on real work. Their projects are very real. So you join us and you get to contribute with the team just as you would as any other team member. Like I mentioned, with our Ignite interns, you are also assigned a mentor, so you can go to someone who's going to be your safe space for silly questions or just getting acclimated to NVIDIA. And then you'll also work directly with the hiring manager who will speak more high level about the projects that you're working on, how you're contributing, and your overall progress here at NVIDIA. Like I said, you don't have to be a part of our intern program in order to be considered for a new college graduate opportunity. So for whatever reason, Ignite doesn't work out and our standard internship doesn't work out, that's totally okay because we also hire new college graduates. Those roles are actually going live probably in the next month or so, and we will continue to recruit for new college graduates through December. And so that's kind of the window, and we hire across a bunch of different disciplines as well. So if you go to the next slide, I know we focused a lot talking about hardware, but these are all the different areas in which we bring in emerging talent. So interns to new college graduates. So yes, we hope you stick with hardware. We hope you stick with computer architecture, but we also do low-level system software, general software, AI, and deep learning, of course. And then we also have, if you continue in your academic career, we also offer PhD roles in academic and applied research. And then wherever your academic journey takes you, we also offer business operations roles as well. And just in the next slide, this will be my last slide. What you can expect in terms of the candidate journey. So essentially the first way to get into NVIDIA is to submit an application. And the best way to stand out is to make sure that your resume, as closely and honestly as possible, reflects the job description that you are interested in. So we recommend keeping the number of positions you apply to maybe 2 or 3 that most closely align with your career goals and your interest and experience. Experience can range from anything from courses that you took, personal projects that you've worked on, anything technical that demonstrates that this is an area of curiosity, an area of passion for you, something that you would like to build upon in your foundation. If you happen to be a match for one of our open roles, then we will reach out to you regarding next steps. Typically, our interview process starts off with what we call a first round phone screen that'll happen over video conference. And then from there, you do a panel interview with the team. That could be individuals stacked amongst each other as in a video conference call all throughout the day, or you may interview with people, multiple people in one interview, just depending on how the team is structured. From there, if you're considered a fit for the team, you'll work directly with your recruiter on your offer letter. And we offer really great benefits to those that join us, both as interns, Ignite interns, and new college graduates. And so if you go to the next slide, the best way to see what we're hiring for, the types of roles that we are interested in, are going to be posted on our jobs page. And so you can check out nvidia.com/careers at any time to see the types of roles that we're hiring for. As you start to progress in your academic journey, I highly recommend finding 2 or 3 jobs that most closely align with your career goals and interests. That's a great way for you to kind of understand how to pick your classes in the next quarter or semester, however you're going to approach that. But those are some great opportunities for you, and we hope that you'll consider us as a potential employer. Thank you so much.
Thank you, Kat.
I was just going to say thank you to both Kat and Ronnie for coming. I'm sure you guys have a bunch of questions following the usual format, although Ronnie has an incredibly hard stop and has to be out of here at 12:30. So if you're going to stay afterwards to ask questions, we'll do it in a group format rather than one-on-one as usual. Otherwise, he'll miss his plane, and no one of us want that. So who would like to ask questions? Well, luckily, Kat here has already taken care of the first question.
There's a question over
Oh,
there.
good. Mm-hmm. Oh, excellent.
Where is it? Oh, thanks. I wrote down this question in the page. Actually, yeah, I'll just ask it from here. Well, first off, I wanted to say thank you for this presentation. It was very informative. I know that NVIDIA used to manufacture graphics cards with multiple GPUs on a single PCB, and also had other technologies for that, such as NVLink, like you mentioned, or SLI. And I know that those technologies have slowly started to get phased out recently due to bandwidth limitations and latency limitations and things like that, and it being hard to optimize the software side of things. Do you see that kind of technology making a comeback with the recent interconnect technologies that have been coming out recently, like TSMC's CoWoS, by any chance?
Okay, that's a great question. All right, so the question is around, I think, interconnect technology and bringing back some of the SLI, and NVLink is still very much a technology that we use, not just to connect, as I showed, chips there, but to connect chips to chips and across GPUs. So that's very important to us. We're also adopting new standards. We adopted Ethernet, and we actually have a very high performance version of Ethernet. And InfiniBand was something that we really latched onto a few years ago, and why we acquired a company called Mellanox was some of their leadership position in that. And recently we just announced co-packaged optics as well, where optics are coming onto the silicon. So we continue to invest in interconnects. It's really critical because it becomes a performance bottleneck otherwise. Yes.
How reliant is NVIDIA or dependent is NVIDIA on Synopsys and Cadence, and why can't NVIDIA perform emulation and verification by yourselves?
Yeah, so question is how reliant are we on Synopsys and Cadence? I think the reliance is really our, in some ways, our choice, because the goal that we have is to focus on things that really, really matter. And we have to focus our resources there. But we really need to help Synopsys and Cadence help them to help us. So what we do now is we work with them to enable their tools to take advantage of this accelerated compute as well. And the emulation and verification tools, as well as the physical design tools, we have a library called cuLitho, for instance, that optimizes and accelerates the compute required for lithography and optical proximity correction. So there's certain parts of things that we think other companies are much better at doing and we don't need to do. Like, we're not going to build a stepper anytime soon. But at the same time, we see if we can help and augment using our technologies as well.
So when it comes to like custom technologies, like you guys developing things for your products so that your people can work better for like accelerators, GPUs, is there any way like students can access like open source versions of those technologies that you create specifically for NVIDIA? Like so that when you guys design them, I guess like an example is like if you guys use like a custom version of Verilog or something like that. Can students, because I have talked with someone before and I'm curious, is there ways to access these tools so that students like me can actually work with them beforehand?
We do open source a lot of our tools. I know in my space we open source an EM solver for a neural network for a 5G stack. But we do open source a lot of our tools. Verilog, I don't know. Verilog's a very specific implementation of chip design. And so there's not a version of Verilog that we open source. CUDA is accessible to pretty much everybody. So getting access to CUDA and CUDA-X is very accessible. But Verilog, I don't think so. I'd have to check, honestly. And by the way, a big focus for us is universities and research. So if you are doing research here, I just talked to a few of the department heads. They do have access to GPUs on campus, which I'm sure is student access.
So on the latest, the 50 series Blackwell consumer GPUs, some of the high-end GPUs were missing some ROPs from the spec that was a little bit different. Do you know any reason why that might happen?
No, I don't. So, you know, production variability, early access, new product introduction. As you guys go through your careers, you'll learn that those are all phases of potential challenges. And I'm sure we've been through those and we'll go through others. But it's a good question. I honestly don't know the answer of those specific.
I can see you're keen to continue the questions. I promise it wasn't the question you asked. I'm looking at Ronnie's time, I'm looking at your time. So I think we're at the end of the class. But if you have further questions, please come up to the front for us. Otherwise, thank you everyone, and thanks to Ronnie and Kat for being with us.
Thank you. Thank you.